Okay, so it's covering section 13.5, and I want to just do a couple of examples here. So in these examples, I want to determine if lines intersect are parallel or skew. Okay, now how can we kind of show that through some kind of analytical means? Okay, we can show it graphically. I mean, just kind of graph it. But now let's look at how can we determine that in a more analytical way. Right? So let's start by defining two lines. I'm going to define L1 to be the vector equation RT equals to 1, -2, 4 plus T 1, 3, -1. All right, and we'll have L2 to be capital R of S, right? And here we'll have 0, 3, -3 plus S 2, 1, 4. Okay. So right away we could see, if it's not clear, we could see that these are not parallel. Right? And the reason that we can see right away is if you look at the direction vectors. Right? So here the direction vector 1, 3, -1 and 2, 1, 4. Right? Those are the two direction vectors, right? The ones with the parameter in front of it. Right? And they're not proportional to each other. Okay. Excuse me. Okay, so they're not proportional, so they are not parallel lines. Okay. All right, so we have two options left. They either intersect or they are parallel. Right. Now, how do we? They intersect or they are skew lines. So how do we determine which of the two they are? Right. So if I take the first one, actually here, let's look at R of t. Let me write it as just one vector. Right. We have 1 plus t, comma, -2 plus 3t, and 4 minus t. And then capital R of S to name my function 2s, comma, 3 plus s, comma, -3 plus 4s. Okay. Excuse me. Okay. So we have two different parameters, S and T. Remember, S and T is just what we call the parameter, right? It doesn't tell me when T is 1, that's just referencing, right? For the parameter 1, if you plug it in, then that will tell you the, not just the vector, but actually gives you the point that is on the line, right? If we think of these lines, they're a collection of points. And when you choose a value for the parameter of T, it is referring to the vector in standard position that is pointing essentially to that point on the line. All right. So if we want to say, all right, do these intersect? So what does that mean? That means do they have a point in common? All right. So in order to try to determine that, we would say, all right, well, let's see if at any point here, right? Remember these functions of x at any point, or when, for what values of t and s are the x functions the same, or the y functions the same, and then the z functions the same. Negative 3 plus 4s. Okay. So we want to find if they exist, right? So now what we have here is we have a system of equations here with two unknowns, but three equations. All right, so it's kind of over-determined, right? So we could see, all right, uh, let's see if a unique solution exists here, or if a solution exists. So I'm going to rewrite these. So I'm just going to write them where all the variables are on the left side, and then everything else is, and the constant is on the right. So that t minus 2s equals to negative 1. 3t minus s is equal to 5. Okay, and then lastly we'll have negative t minus 4s is equal to negative 7. All right, and I want to solve this system. Now, however you want to solve this system, elimination, substitution, I personally, when it's more than two equations, simply just prefer using an augmented matrix, where the first column is the coefficient of the t variable, the second column is the coefficient of the s variable, and then the last column there is what's on the other side of the equal sign, right? Essentially the constant terms. All right, and then I like to just actually plug this into some calculator, right? Put it in reduce row echelon form. Right? Usually in my TI-84, although there are online calculators that will do this calculation for you. And then here we'll have 1, negative 2, after it performs all these matrix operations. 2, 0, negative 6, negative 8. Okay. So we left this, right? So now we want to interpret that. Okay, so what this reduced row echelon matrix is telling me is that I'm going to look at these two rows here. All right, and I want to interpret that. Remember, that second column is the coefficient of the s variable. So what we have here is that negative 6s is equal to negative 8, right? That is row 3. And in R2, we have negative 5s is equal to 2. All right. Now solving for s, we get s is equal to negative 2/5, and we have s is equal to 4/3, right? Or 8/6. Okay, so that means that in this particular case, we have two different values for s. Now, the way I want to interpret that is when this happens, is this is telling me that there is no solution for this system, right? S can only be one value, right? And the way I want to interpret this is, all right, I have two different values. So the conclusion that this is leading me to is that R of S and lowercase r of t are skew lines. Okay. So again, right, we determine in the very first part of this problem is that they are not parallel. They have direction vectors that are not proportional to each other. We try to solve for unique values of s and t. That is not possible. So then that leads me to the conclusion that they are skew, right? And if we look at the graph here, so what you see here are the graphs of these two lines that we're working with. And you see they exist on different planes. So they are, in fact, skew. All right, not parallel, right? They're going in completely different directions, and we knew that because of different direction vectors. But they also do not intersect. Okay, and again, right, that was trying to solve this system uniquely, and we are unable to do so, right? Because I get two different values for my parameter s. Okay, let's do one more here. One where we do come across when in fact they do intersect. So let's look at this example here. And I want to determine if lines are parallel, skew, or intersect. Okay. All right, so again, let's define L1 to be R of t equals to 1 plus 6t, 3 minus 7t, and then 2 plus t. All right. And L2, we use capital R, S. And then here we'll have 10 plus 3s, 6 plus s, and then 14 plus 4s. Okay. Excuse me. All right, so once we are here, let's so we have the two equations of the lines, and let's see if they are parallel. So let me write down the direction vectors. For R of t, the direction vector is, and again, you can determine that by looking at the coefficients of the parameter t, 6, -7, 1. All right, and then for R of s, we get 3, 1, and 4. Right, and we can see right away, right, if I multiply the second one by 2 to match up the 6, I don't get -7 and 4 in the other components. So right away we can conclude that they are not parallel. All right. Okay, and again, that's a symbol for parallel lines. So they are not parallel. So they either intersect or they are skew. So let me determine that here by setting these equal to each other. So 1 plus 16 equals to 10 plus 3s. 3 minus 7t is equal to 6 plus s. And then 2 plus t equals to 14 plus 4s. And again, writing it where all the variables are on the left and the constant on the right, we get this to be 6t minus 3s equals to 9. -17 minus s is equal to 3. And then t minus 4s is equal to 12. Okay. All right. And again, my preferred method is setting up a matrix. It's just way easier, in my opinion, here, especially if we have technology at our fingertips here that we can solve this problem. All right, and again, we reduce row echelon form. All right. Excuse me. Okay, so we reduce row echelon form, and here we get 1, -4. This guy 12, 0, 0, 7, -29, and -21, and then 87. Okay. All right. And I notice here again, similar to what we had last time, we had -29s. We have two different equations for s, but something different happens here. Right, solving for s, we get -3, and then the other one, we divide by -29, -3. Same. All right, so now that means that we have the same value for s here. So what this is telling me here is that I can solve uniquely for s and t. All right. So I know the value for s is -3. How can I find t? You can look at this one here. And again, t minus 4s is equal to 12. All right, that's what that first rule is telling me. All right, remember, coefficients. Okay, and solve for t. I know what s is, right? So t equals to 12. All right, and then here we have plus 12 minus 12, t is equal to 0. Okay. All right. Now, we found the parameters s and t. Notice we do not know the point of intersection. All right. Remember, the parameters are just relative to the equation, right? If you recall here, these vector equations, the way we arrive at a vector equation for a line is we need a point on the line and a direction vector. So there are infinite points on the line, and you can use any multiple of the direction vector to represent that same line, right? So, and then that means that different values of parameters will give you different points on the line, right? So I've determined that they intersect. But now how do I find that actual point of intersection? Okay, so we determine here, so what this is telling me is that the lines intersect. All right, but now I want to take a step further and say where. All right, so let's use that parameter to determine, all right, what is the point of intersection, right? Remember, these are vector equations, so when you plug in the 0, you get a vector, but remember, that is the tip of the vector, right? And if the vector is in standard position, right, it is also the point of intersection, right? So r of 0 gives me 1, 3, 2, right? So the point of intersection, 1, 3, 2. Right, and again, just so we are clear here, let's double check here. R of negative 3 should yield the exact same point, right? So we get 10 plus 3 times negative 3, and 6 plus a negative 3, and then 14 plus 4 times negative 3. And you see here, 10 minus 9 is 1, 6 minus 3 is 3, 14 minus 12 is 2. Okay, so we see they are in fact pointing at the same point of intersection, which is what we concluded here, right? This is just kind of double checking my work. All right, and now let me look at a graph here. All right, and you can see there that these lines live on the same plane. All right, they're not parallel, then they intersect. All right, and then here let's look at 1, 2, 3. Oops, 1, 3, 2. There we go. All right, and you see there's our point, P of intersection. Okay. All right. Okay. Now, what about this brief discussion of other curves besides lines? All right, and again, keep in mind that our formulation of a vector equation is some function x of t, y of t, z of t. All right, now when it's an equation of a line, those x, y, and z, there's one independent variable, right, that being t, and when they're all linear, we get an equation of a line. But they don't have to be linear, and that leads us to different types of curves. All right, let's look at kind of a simple example here in, let's say, R2, where when we talked about parametric equations, right, we had a circle here, and we can define the circle, and again, even the unit circle, if you think of it, is a parametric equation, right, where the points on the circle can be defined as cosine t sine of t, right? When the radius is 1 here, that's what we call the unit circle. Okay, and then that gives me all the points on the line there, right? And we can kind of extend that here to, let's say I had it in 3 dimensions. Okay, so again, just a basic curve, just so you could see we can actually generate other curves by making the functions, they don't necessarily have to be linear, right? And what we would imagine here, we say, all right, z is 0, so that is actually, this lives in the plane, so keep in mind here, z is equal to 0, so that lives in the xy plane, right? And it's still that same circular curve, right? So if I look here, let me turn these off. All right, let me do this, and you see, all right, there is our circle in the xy plane. And again, you can play around with it. You could kind of do different things here. Let's say you wanted to have it in a different plane. One thing you can do is you can do something like this, right? And now notice here y is 0, so we're living in the xz plane, right? And if we do that, let me play around with this here. Right, 0, okay, and then there you see it changes its plane. All right, and it doesn't have to be in the axis. I could change that 0 to, let's say, 3, and then it moves it to the plane. In that case, y is equal to 3, right? That's that plane that it's living in here, right? And I'll draw that plane here, y equals 3, and you see there, it's living in that plane. Okay, and you can mess around with, it doesn't necessarily have to be parallel to any axis. You could say, all right, what if we made it minus sine t, right? And then you could see there, it tilts the axis a bit, right, by playing around with it there. All right. Okay, so you could see here other curves, and again here we're just playing with just a very basic circular curve, and you can also generate, so let's going back here. All right, you see, okay, this is our circle that kind of lives in the xy plane when the z component is 0, right? But let's say I made that z component in my equation the parameter t, right? And I kind of want you to visualize what is happening here, right? So now that third component is not fixed, right? The x and y want to go in a circle, but the z is increasing, right? So a couple things about this function curve in GeoGebra. It works a lot like the functions that we're using now, right? Where the first component is the x, y, z. That fourth component is where you define the parameter. In this case, the parameter is t. And then the values for the parameter go from 0 to 7 in this case, right? Usually when we work in our, unless explicitly stated, we assume t goes from -infinity to infinity. In this program here, we have to actually define for what values we want it to take on. In this case, I put 0 to 7, essentially between 0 and 2 pi. But here, what happens, back to this problem here, what happens when I let t be variable? It's no longer living on a plane, right? The z is also changing, and let me hit enter here. And what you see here is a helix, kind of like a spiral. And let me make it a little more dramatic here. All right. Okay, and you could see that as the x and y are going in a circle, right? Those are periodic functions. The z kind of stretches it out along the z-axis. Okay, so to wrap this section up here, I want to define here, similar to Math 1, right? The idea of limits and continuity. All right. Okay, so what does it mean here when we have r of t to be equal to some function, right, x of t, y of t, z of t. Okay. Okay, so what does it mean to say something like this, right? The limit as t approaches a of r of t. Okay, now in this case here, it is based on the parameter t, right? Not a particular point, but the parameter. Right, and we say, okay, the limit as t approaches a of r of t is equivalent to taking 3 limits, right? Where you just take component-wise, right, what is happening to each one of these functions as t approaches a. And then from there, all of the techniques that we use in our first semester calculus are still valid. All right. And let's say that each one of these limits exists. We'll call them L1, L2, L3. And that would be equal what we'll define the constant vector. Okay, so that's how we can define this, the limit of this function. Right? And if they exist, all these limits L1, L2, and 3, all 3 of them exist, then we could say, all right, that function is continuous when the parameter t approaches a. All right. Thank you.